Hello, everyone. Welcome, everyone. My name is Andrew Harris from Epic Games. It's great to be here to talk to you this year about our ongoing digital human effort at Epic. A lot of you have been following what we've been up to for a while, but let me just recap some of the ground we've been covering in this exciting area of real-time computer graphics. You've all seen the kite demo we did a few years ago. Back then, it was incredible to see a character of this fidelity with a fax-based facial rig having such rich animation controls and able to perform in real time. Up until that point, this just hadn't been possible in a game engine. Since then, we've been pushing quite a bit further. So in terms of stylized characters, Fortnite has been and continues to be an opportunity for us to push even further into the style and visual territory of high-end animated features. We again incrementally improved skin and subsurface scattering, and we experimented with stylized looks for things like the eyes and the hair. With the facial rigs, we went much deeper into designing a rig that could achieve an even broader range of motion and utilized alembic caching to bring into engine a far greater number of deformations than would have been possible otherwise. This was all really great, but we really wanted to push even further. So while we had a team working with stylized characters in Fortnite, our Paragon and Special Projects teams got busy refining the process of creating photoreal digital humans, starting with the most scientifically accurate procedures for scanning and measuring our real-world actors, and then using that data to create the most convincing digital characters. Twin Blast, a character from our game Paragon, was an early example of this work that we released to the community a little over a year ago. Around that time, you might also remember that we partnered with Ninja Theory to help them realize their character of Senua from their game Hellblade. Both of these characters broke new ground by utilizing techniques previously only employed in high-end film effects. Now, additionally, we began to form a strong collaborative partnership between Epic Games and the leading companies in the world who are able to do this level of work in real time, 3Lateral and Cubic Motion, both of which you're going to hear a lot more about in this talk. Now, last year, we decided we wanted to go even further. Could we take what was done in Twin Blast and Senua and improve upon it? And could it be done in VR? This was the new challenge for us leading into last year. And the result was a demo for SIGGRAPH 2017 called Meet Mike, featuring Mike Seymour of Effects Guide fame, who worked with us as a model and reference and as performer. And we used all of these evolving techniques for modeling and performance capture. Mike was created as a digital human who could interview guests in real time in VR. And the research for this project was sponsored by Tencent, and they worked very closely with us on the look development for Mike, and also on our follow-up project, Siren. Siren is a full digital human bringing together all of the latest scanning, modeling, rigging, and rendering techniques, and being performed in real time and rendered in real time for a room full of people who could interact and talk with her live on a screen. Now, this should pretty much bring us up to date, and Siren was sort of the culmination of all of our digital human work and research up to this point. But then just these past few months, we had an opportunity to push a little further. So we turned to a friend of ours who happened to be no stranger to digital recreations, an actor who many of you know, Andy Serkis. Now, Andy was kind enough to allow the teams at Epic, 3Lateral, and Cubic Motion once again to poke, prod, measure, mark, model, rig, render, and animate him using everything we've learned up to this point. The result has been a project that we've been really excited to demo this year, and we hope you've all had a chance to see it during the keynote. And if not, we're going to show it to you again in just a moment. So now, not only does this show a great example of both human and non-human photo character work, but also how animation can be shared between dramatically different characters, especially when they share the same core architecture. So let's roll that video.
Tomorrow, and tomorrow, and tomorrow creeps in this petty pace. From day to day, to the last syllable recorded time. And all our yesterdays have lighted fools the way to dusty death. Out. Out! Brief candle! Life's but a walking shadow. A poor player that struts and frets his hour upon the stage, and then is heard no more. It is a tale told by an idiot, full of sound and fury, signifying nothing.
So you guys probably didn't expect to see Shakespeare coming to GDC this year. But with that, I want to introduce you to some of our key members of this team who will be talking to you today. Adam Scott will be here to tell us all about his approach to handling this kind of data, the massive amount of data we collected, and what went into modeling and texturing the characters. Peter Sumanaseni will be taking us on a deep dive into the materials and new rendering technology that was used. Chris Evans will then be up here to take us through the rigging, simulation, and facial setup. And finally, James Golding will join us and tell us all about LiveLink. But first, I'm going to talk a little bit about our scanning and data acquisition process. So in order to achieve final results like the ones we're showing today, it all starts with the scanning and data acquisition process. Even in the case of non-human characters, real-world reference is indispensable. We've been working closely with a company named 3Lateral for several years now, and 3Lateral specializes in digital humans. Well, actually all life forms. They're not that discriminating. They've become one of our closest partners, and we relied on them today for the data acquisition and facial rigging that we're talking about today. This was the actress, Bing Jie, who we recreated digitally for Siren. And these are her teeth. The process we used to capture her likeness was similar to what is done for your favorite actors for big summer blockbuster movies. She performed with dozens, or actually hundreds, of cameras and sensors suspended all around her. They were able to capture detail from every angle. For areas like the teeth that weren't always visible, we even scanned her dental molds. Similarly, for her head and face, we captured her performing 50 fax poses. Each pose helps us to isolate the movements of different muscle groups in the face. We also used the imagery from these scanning sessions to create physically accurate data for use in our diffuse, normal, specular, ambient occlusion, and translucency maps. We also captured 4D reference, which is essentially a 3D model for every frame of a performance. For Siren, this provided us with great ground truth reference to compare the animation rig against. Cubic Motion would track the facial performance and drive 3Lateral's rig to try and hit all of the right poses. And we would always compare the results of the animated rig to the 4D data. Here's the 4D scan of Bing Jie. With Andy, we captured even more. In fact, check out how much higher fidelity his 4D capture is. You can see it has a lot less of the 3D noise in the model. There was a reason for this, because beyond just wanting good reference, we wanted to be able to actually drive the rig with this 4D capture data, rather than just using it as reference. So this was going to require a lot more resolution than we used with Siren. Something you'll hear a lot about in this talk is microgeometry, and that references to all this incredible pore-level detail that we capture. A huge part of making these characters convincing is being able to really capture those tiniest subtleties, including how the pores squeeze and stretch as the face deforms. By capturing all of this in incredible detail for every pose the actor makes for us, it allows us to blend and animate between all of the different maps to create a convincing effect for every possible performance. Here's another example that shows even more clearly the way the micro detail changes as a person moves their face into different positions. Okay, so with that, I'd like to introduce you to Adam Scott, who's going to take us through his modeling and texturing process and explain how he starts to make sense of all this data that we've just acquired. Adam? There you go. Welcome.
Thank you, sir. So, hey guys. Our goal here was to basically create digital doubles in order to research and improve our character pipeline. Whether it be modeling, shading, or animation, we needed to be able to compare results to real-world reference photography in order to properly vet the work that we were doing. We started with Mike Seymour dataset from ICT. The scan data is the closest thing you're going to get to a ground truth in 3D, so every adjustment or cleanup pass that is done on the modeling side is going to be an interpretation of how it should be, and will affect animation and material comparisons moving forward. So it becomes the artist's job not so much to sculpt a sweet character, but to maintain the integrity of the scan, and to supplement or correct where the system can't reach. There can be parts of the face that are often occluded from the camera's view during the scan. So common areas tend to that tend to need cleanup are upper eyelid, under the brows, ears, scalp, neck, and chest if there's a shirt covering that up, or if you're working on a body, fingers, toes, or anything with undercuts. And this is where a bit of artistry and anatomy knowledge and good reference captures will be critical. The goal being to sculpt out the areas of the skin that were not captured well without messing up likeness or breaking any anatomical structures. So I use sculpt layers in ZBrush. They are extremely beneficial for projects like this. When separating artistic interpretation from computer-generated data, it's a necessity. I know ZBrush has like 10,000 undos now, but trust me, using layers is much, much easier. The displacement map created from tertiary normal information during the scan process, the object normals are captured from multiple lighting directions, then that information is converted to a displacement map. And this encompasses all of the tertiary details. This map can be applied in ZBrush or Mudbox, whatever software you prefer, and while the accuracy of the scanned forms, the macro details, are ground truth, the intensity of the tertiary detail captured from the normals is arbitrary and needs to be matched from reference. So texturing XYZ in services like surface mimic displacement were used to fill in any scanning areas that the cameras could not get to. Again, it's important to have these hand-placed details on their own layer. One other thing, some benefits of applying everything in layers is that you have control over the intensity, and you can bake these details into their own maps. So you can use them for things where you need to share different aspects of like pores and wrinkles across several different characters. So from left to right up here, you can see, and this image shows the raw Andy scan, triangulated mesh, like totally raw scan data, in ZBrush. And then the middle image is new topology with scan details projected and cleaned. And lastly, the displacement map is added, which captures all of the tertiary details. So you can see how much awesome information you're getting from that tertiary detail scan. Andy was done completely at 3-lateral from scanning to final model, and the Mike Seymour scan was used at the light stage at ICT, and then the model was cleaned and finalized internally at Epic. So the texture maps here are a mix of scan-generated and artistically generated maps. So the albedo is captured during scan time, and for the albedo map, we project hair from the reference photography back onto the scalp and clean up any areas that require it. Painting software of choice for myself was Mari, but it's totally feasible to use something like Substance Painter. The normal information consists of 2 maps. The base map is baked from our high poly model. The second normal map captures the detailed microstructure of the skin. And then we also create a mask to reduce or remove the micro detail on certain areas where it was giving too much breakup. For instance, the tip of the nose where the skin is very tight, the crunkle, which is the tear duct, lips, and inner eyelid areas. We also baked a thickness and ambient occlusion map to control forward scatter. We painted some regional masks to help control additional roughness and scatter regions, and then also a cavity map from ZBrush and a hair AO for the scalp to provide control for specular occlusion. And Pete will go over more of this information later in the materials portion of the talk. And here's just a quick glimpse of some of the maps that went into creating Andy. So our real-time model. We had a pretty generous poly budget when creating these characters. We knew pretty early on that we wanted to use individual hair strands rather than cards, and that the poly count for those would probably be quite high. Knowing that, we weren't quite as concerned for the amount of polys we put into the face. There just had to be enough loops to deform realistically while still being at a reasonable level for artists to work with. So the final try count for the face meshes varied between 40,000 and 43,000 triangles. The mesh needs to be aligned with the anatomical features of the face. The perfect edge flow is debatable, but there are similarities between commonly used flows. For example, radial flow around the mouth and the eyes, loops that define the nasolabial fold of the face, and a grid-like flow on the forehead. I do believe there are areas that could be improved on here. Under the eye, if you look at how the wrinkles are running perpendicular to the mesh, there are edge flows that follow those wrinkles much closer. And I believe you'll get a better deformation under the eye, but it's something that we're still testing out going forward to find like the the best topology we can work with. Also, it's very important to align the mesh with the baked normals. For example, the nasolabial fold, you can get some pretty bad normal stretching, especially with a lower poly mesh, if these edges aren't lined up properly with the normals. And a quick note, same topology was used for Meat, Mike, and Siren. Andy, being the latest, had an updated version. So here you can see the differences between Andy and Mike Seymour. You can see Andy is a bit denser around the neck and forehead, and poles have been removed around the chin and sides of the nose. But overall, they are fairly similar. So the mouth and eye setup are similar to what was used for Paragon, with some additional mesh pieces in the mouth. We have an eyeball geo with a corneal bulge built in. There's also a bit of a bulge on the nasal side that was present during the eye scan data. The caruncle, which is, again, the tear duct, is built into the head mesh, so you won't see it here. The caruncle's blend geo, which helps soften the transition to the eyeball. Next, there's a lacrimal fluid mesh, or the little bit of wetness that pools underneath the eye and the lower eyelid. And lastly, for the eye, we have an occlusion and blur mesh that Pete did all sorts of fancy stuff with to help seat the eye better into the head. For the mouth, we have the gums, tongue, teeth gum blur mesh, which is a mesh that helps blur the transition from the gums to the teeth a little bit better. That's similar to what was done for the eye. And lastly, for the mouth, we have tiny saliva bubbles that were modeled, as you can see there. So all of the hair was created with XGen. For the Meet Mike project, I used the interactive groom splines to shape and style the hair, along with a guide modifier. And if at any point I need control over individual strands, you can simply just mask out that modifier. During the Siren project, I went back to the traditional XGen tools and placed guide curves by hand. I feel I had more control over the longer hairstyle this way and was able to use expressions to control different things like strays and then the noise attributes based on length. Primitives were converted to thin poly strips. So in XGen, all of the primitives are going to automatically billboard to the camera. So to bring them to engine, we had to turn face camera off before we converted to the poly strips. So the billboarding was handled in engine, and all root tip variations such as like width and taper were also disabled, and this was handled in engine as well. The hair strands were layered over the cards for Siren. They originated from the center part of the hair in the front and temporal region of the hairline. Layering it this way helped hide the card transitions where they met the skin and made sure we got the most coverage out of our hair strands. And we did this to reduce the poly count for Siren's longer hairstyle. Multiple UV sets were used to control hair attributes. So you can see those here. UV set 1, the first UV set is auto-generated by XGen. As long as all of the tiling options are turned off, each hair strand will be overlapping. Here, each UV shell is overlapping, and we use it to globally control attributes like root, tip, width, and color. UV set 2. The second UV set basically gives regional control for things like hand-painted masks, or if we want to add like a noise for color variations, we could do it here. We had some tricks to generate the second UV set. First, we would convert the groomed XGen primitives to geometry using the default UV settings. Next, I would reselect my XGen groom and add a length modifier to shrink the hairs down to be very short, think like stubble short. Because XGen does not change the topology or vertex order based on length, you'll be able to create a blend ship later on. Then convert the shortened groom to polygons as well using the same default settings. We now have two sets of hair geometry. One is the manicured groom, and the other is the super short hairs. Create a second UV set on the shortened hair. Do a UV transfer from the scalp geometry, which the hair is growing off, and then transfer the UVs in world space. So the last step is to create a blend shape between the groomed hair with the overlapping UVs and the short hair with the scalp type layout. And then what you have is like, you know, one hair mesh with the two UV sets. One is like a global like type UV set where you can just do everything and it affects every hair, and the other one is where artists can go in and hand paint or add like, you know, noise and masks and all sorts of things. And thirdly, the last UV set there was for us to bake individual AO for each hair strand. The only caveat there is that the map had to be pretty large in order to get enough pixels to, you know, capture that AO. So here's an image of the Mike Seymour hair groom in Viewport 2.0 in Maya. I should mention too that within Maya in Viewport 2.0, it was super beneficial to be able to see how, have a real-time update of the groom. There was no groom, render, wait to see what it looks like. It was just instantaneous feedback. So textures for the hair cards were also created with XGen. You can see here the hair descriptions were growing off the slanted planes, which I then rendered using Arnold. I use the slanted plane because it gives more of a dimension to the texture and kind of mimics the slope of the skull. And that way all the hair roots aren't originating at the same horizontal axis, and it kind of helps avoid that dull type look with hair. So this workflow is really quick and super flexible. Using modifiers within XGen produce really fast results and allows me to quickly iterate on the look of the hair. For example, if I needed the hair to have more frizz or be more curly, it's just a matter of a few curves and numbers or adding an extra couple modifiers. Another benefit is being able to render out passes. So for Siren's hair textures, I rendered out 4 maps out of Arnold. So there's diffuse, ambient occlusion, alpha map, and root tip gradient. The diffuse was pretty flat aside from some strand color variation baked in. All the specularity was handled in engine. Ambient occlusion was used for specular occlusion and a slight multiply on the diffuse to add more depth, and the alpha was used for opacity. Root tip was used for blending to the scalp as well as tip color variations. And then all the cards were just placed by hand. So I've tried a few different methods where you can use instance geometry as cards, but there's always a lot of cleanup and interpenetration, so I always just find that I get better results by just taking the time to hand place. And this slide just shows the kind of thought process behind putting Siren's hair cards together. So you can see on the left-hand side, cards, and then the peach fuzz. Middle, there's the main strand clump, and then we have flyaway hairs right here, and on the last end there, it's just some transitional hairs to kind of help blend everything together. So, cloth modeling. We had different needs for each project in regards to cloth modeling. We didn't need any dynamic cloth for Meet Mike or Digital Andy, so they were pretty straightforward. Created their shirts in Marvelous, and then did a detail pass over top in ZBrush. And generally, this is the approach that I'll take for any cloth that doesn't need to be dynamic. Siren's dress had to be dynamic and move in a realistic way. So we captured a ton of video reference of Benji, the model, in her dress, moving around so we could see how the fabric moved with her. We came to the conclusion the dress only needed to be dynamic from the waist down because it was pretty form-fitting at the top, but we'd probably need some subtle wrinkle maps and correctives around the flank areas. So it was started in Marvelous, but only to get a quick base. The majority of the work for her dress was done in ZBrush because there really wasn't any draping in the neutral pose, and the dress had to be splayed out in engine for it to simulate. So here's how her dress was modeled. So all the wrinkles you see when you see the demo is just engine simulation. And then here's a close-up of the dress material, and we just simply used texturing XYZ tiling maps for the cloth details. So sculpting and characterization. All of this information can be used across many different types of characters. For example, the Osiris model shown here, which was made by the folks at 3L, is not a scan of a real-life alien. He was the creation of talented artists. A lot of the believability comes from the skin detailing, which is generated by the scanner. But if you don't have access to a scanning solution, there are services like Texturing XYZ that have a library of scanned surface details and textures. Because we have been comparing real-world photography as reference, deficiencies within our models, shaders, and textures have been pretty easy to spot. And so now that we have spent the better part of a year improving on those aspects, really the sky's the limit on what artists are able to create as believable real-time characters in Unreal. And I just want to leave you guys off with this image, which I think this character is awesome. And it just shows off the culmination of efforts for Osiris, and it's pretty sweet. So next, I'd like to introduce our senior technical artist, Peter Simnasani, to talk about materials and look dev. Thanks.
Good job. Hey guys, I'm here to talk a little bit about look dev for real-time digital humans. So going into this project, we had a couple goals. The first one was to use high-quality scans to see how far we can get in the engine to making a believable character. And in that process, we wanted to learn and improve our rendering technology and also some of the material templates that we use in Unreal. In this talk, I'm going to go over the look dev environments, the rendering improvements, which will be released in 4.20, and some of the material templates that I've developed along the way. So with look dev environments, the first thing we need to do is prepare all our reference. With any reference, we want to make sure we capture a proper Macbeth chart, do the color calibration, have it, make sure it's in sRGB linear. And in the engine, we also want to turn off any tone mapper and have our engine run in sRGB linear so we can match 101. You can see on the left here what the tone mapper does to Andy compared to tone mapper off and the real reference. So our first look dev environment that we worked on was to match the multiple single light reference. Here's our friend Mike Seymour with ICT capture. And we use this to match specular values, scatter values, normals, and backlighting on the ears, and how light behaves on the hair. So in the engine, we take that reference photo, and you can see the reference is on the left, and our Unreal Engine image is on the right. And we take that in engine, and we're dialing it in real time to get a match. And here's some different angles of Mike. And I think we matched it pretty well. It's kind of almost not discernible from a distance. You can see his pupils are a little bit differently dilated, so that's a giveaway. So our second look dev environment is the light probe reference. We like to capture light probes of our character in the sun, the shade, and indoor or studio environments. And this is to test to see how well we did with our shader. We want to make sure that it doesn't just look good in a single light environment, but multiple light environments. And we can use this to test our dynamic skylight in the engine, make sure our bent normals are working properly. For these images of Andy, I actually important sampled IBL and made a bunch of lights around Andy. So it's about 64 lights hitting Andy. In the future, with ray tracing, we should be able to use those IBLs directly. And here's a reference photo of Andy. This is on the roof at 3 Lateral. So some of the rendering improvements that we made along the way. We're going to favor a double Beckman specular model. And we're choosing Beckman instead of GGX because Beckman is a little bit tighter in its tail, and it worked a little bit better for our double lobe model. And the double lobe is there to mimic the sub-pixel micro-frequencies in the skin. You can see here's like a rougher specular, a tighter specular, and combined, it gives us a lot more detail and believability. We're going to release backscatter in our lights. It's actually forward scatter because light is being scattered forward to your eye, but we call it backscatter because it's a backlight effect. And it's pretty simple. We're using a classical single scatter. We sample depths from shadow maps and run it through a colored exponential fall off. Then on top of that, we run it through a phase function and use the index of refraction vector on the phase function to give it a little bit more shaping. And you can see Benji here with no backscatter and backscatter on. So it just gives a little bit of extra believability in our characters. So we are also running scatter on the teeth, but we quickly found out when we scattered the teeth, we had halos around the teeth where, since we're doing screen space subsurface, the light from the lips were kind of blending into the mouth, causing like a halo. So we came up with this idea of a boundary bleed color. And you can see here, we can actually define how one subsurface scatter material bleeds into another. So if I go back and forth, defining that color really seats the teeth in the mouth with our screen space subsurface. For the eyes, for our template, we added subsurface scattering and also the ability to do an iris normal. And that's been a requested feature. So just gives a little bit more detail on the iris you can see here, and directionality from the lights. One thing that I always find missing in CG humans is the lack of indirect bounce from I call it self-irradiance, but it's the light that bounces from your cheek to the corner of your nose or in your eye sockets. And if you don't have that in your character, you get what I call CG gray, and it's just a lack of nice soft bounce, but also it has this contrast where you kind of instantly say, oh, that's a CG video game looking character. So we developed this idea of a screen space irradiance. You can see I'm turning it on and off. And it really fills the character, the eye sockets, the nose becomes believable now. You don't have that sharp contrast around the nose, and the lips gets a lot more fleshier. So I'm going to go over some of the material techniques that we used. Our normal maps, we split out into two normals. We have a micro normal and a meso normal, which is the medium-sized details. The micro normal is used to break up the specular. For Mike Seymour, we got the data from ICT, but on other characters, you could extract it with a high-pass filter from the specular and run that through a normal generation. You kind of get variations in the skin. The mesonormal, we usually capture that in animated poses. So here, we're using all the animated poses that we captured from Andy, and we split it into 4 different normals, and they're driven by animation. So when Andy is acting, it's triggering these different normals to be activated. And in the middle, you see there, that's the mask that it's being used to drive different normals. And for our roughness, we are actually not painting roughness. There's this technique called normal to roughness in the engine. Any texture, if you look on the bottom right-hand corner, there's a little box to put in a normal. And so our method was not use any normal at all. We start with a black texture and put in this normal to roughness, and that became the basis of our roughness. And since we have animated normals, it also gives us free animated roughness, which is pretty neat. So these two techniques combined together forms the basis of all our roughness. So the micronormals on the bottom and the animated mesonormals on top there. And we quite couldn't capture every single detail with a scan. So there is nano roughness variations in the skin where we just can't capture that with a camera. So what we do is we paint different regions on a face and use those regions to kind of, with our reference, to eyeball the exact roughness so it matches. In addition to that, we also add a little bit of Fresnel on the edge to mimic fuzz. So with skin specular, we start with a constant. We don't want a painted specular. Painted specular variations aren't PBR. So it's just based on the index of refraction of skin. But for the engine, we actually can't ray trace every single displacement. So we want to include that specular so it's a little bit broken up. So we use a cavity map generated from ZBrush to use for a specular occlusion. In addition to specular occlusion from the cavities, we have to bake the hair onto the specular, because the hair we do isn't as thick as real hair, because we can't afford to make it exactly like real life, so some light gets through, so we're just baking that into our specular. And here's the specular mask for Andy. For the hair, it's all polystrips, so this lets us do a combination of painted hair and procedural hair. Like Adam showed, we lay out the hair based on the scalp. That means the painter can directly affect the hair based on location on the scalp. On the right here, you see this is Andy's gray hairs. Then we add per hair noise variation and also vary along the length. In addition to that, a hair is not a perfect cylinder, so we want to vary the tangents along the length. So I call that scraggle. With the fuzz material, we tried at first to use the regular hair template, and it didn't work out that great. You kind of want fuzz to be really subtle, and when we used the hair template, it was kind of specular all over the place or dark all over the place. So instead, we favored a translucent material, and what we did was sample the color behind the hair and then darken the roots a little bit and brighten the tips, and that gave us enough subtlety to be present but not kind of overtake the image. And I think it adds a lot to the final image here. You see the hairs on her face. So now I'm going to introduce Chris Evans, our lead technical animator, to talk a little bit about rigging. Thank you.
Hey, how's it going? Wow, that is a lot of people to hear us talk about lacrimal fluid, let me tell you. So the guys have really talked about a lot of the details that went into making believable characters. I'm going to speak a little bit about how we get all of those details moving. How we deform all of the meshes and shaders and everything that they've just spoken about. So a few years ago, we worked with Weta on the smog demo. Smog was about 400,000 deforming vertices. The character was the size of a building. We thought it was the highest res character that we were going to be working on. We had to improve a lot of pipelines to deal with that. Well, Siren is about 700,000 deforming vertices. This really made us have to rethink some of our pipeline steps. Just the FBX intermediate that we kick into Unreal was about 4 gigabytes. I'd say most of this was the vellus hair. That's the peach fuzz that Pete was showing. It really looks amazing, and I have never been able to work on a character that had vellus hair. I mean, I've worked at a lot of places on a lot of projects, and you try to, you try to fake it in shaders. You try to, it's very, very difficult because every single hair has to ride along on the surface of the face. Why is that difficult? Because Siren is live, she has to do every facial expression, every micro expression that the actress can do, and that Cubic then sends through to the rig. What that means is a single polygon of the face can have an innumerable number of blend shapes that have to fire and address that. Well, if you have multiple vellus hairs that share that polygon, if at any time they poke through the surface of the face, you're going to get shimmering. It's going to fall apart. When you look at some of the places you see it in the most detail is around the silhouette. And those silhouettes, if you have hairs that are poking through, it's all going to fall apart. So what you basically have to do is you have to sample every facial action, the accumulation of every morph target that can act upon that polygon. And then you need to kind of do a weighted sampling and figure out the exact blend shape weights that every hair is going to get. And this is something that 3Lateral spent a really long time on. I've worked with them on multiple projects where we tried to do beards and vellus hair, and we've never been able to do it until this project. Adam talked about like the wetness meniscus, the saliva in the mouth. I was troubleshooting something with her lips, and I was looking inside, and I saw saliva bubbles in the teeth kind of early on in the project, and I was just like, really, guys? Really? But that's one of the great things with working with these guys. I mean, they set us up like, hey, the saliva bubbles are there, now we've got to render them, and then Pete's like, oh, okay. So I talked about about like the deformation itself, but I want to cover what's driving it. This, you see, is a rig running in Maya. I play blasted this rig because this rig, with all the deformation I talked about, runs at about 10 hertz in Maya, 10 frames per second. The entire rig using 3Lattice's rig logic is running in UE4. It runs at 60 hertz, deforming all of the meshes we talked about. The entire rig itself, which is hundreds of thousands of DAG nodes in Maya, evaluates in under a millisecond in UE4. And we really have to have the rig live in UE4 because Cubic Solver solves directly onto the animator-facing rig controls. So Cubic Solver is live solving onto the same animation interface that an animator uses. And that, in turn, is driving about 725 blend shapes. The 725 blend shapes, they're across 10 meshes, so that's when you start thinking about this 4 gig FBX file. There's thousands of blend shapes that are coming into UE4, and over the years, from shipping the Boy, Senua, Mike Seymour, all these projects, we've really, James and his team have made a very, very big push on getting blend shapes to run fast in the engine. I spoke about runtime rig logic. There's about 185 rig inputs, and those are evaluated to about 760 outputs. That's all of the main blend shape curves plus a bunch of driven maps that I'm going to talk about in a minute. This was one of the first times that we handed off animation data to the engine via FBX in only controller data. And to the animators or riggers in the audience, you can see the controllers moving. 185 floats in an FBX is a lot smaller than 5,000 floats in an FBX being animated. And it was really great to be able to just send over the animation controller data. Hey, we have the rig here. Hey, we have the rig here. Let's just send over the rig controls the same way that in the past we've been sending them across the network using LiveLink. One thing I want to talk about is the body. So this is actually a video that James presented last year. We were working together on Paragon. Morigesh was one of the characters I worked on. And we thought she would be a really great example to use as kind of a complex gameplay example for the pose driver. He talked about the pose driver then, and we've worked on it a little bit since. So basically, it's a radio basis function pose driver. We used it on Siren to drive about 30 different poses. Some of those poses were arm fixers. Here you can see Jared, one of our really talented artists, he created a fixer for the elbow, but we wanted to drive multiple fixers because she doesn't just walk around like this all the time. She sometimes would stand like this. You can go talk to her at the Vicon booth. With the head here, you can see we used multi-joint driving, and I just spoke about pose intermediates, actually. I'm getting ahead of myself. But with multi-joint driving, we can not only drive a pose by looking at multiple joints, but we can also do things a little bit simpler. If you've ever tried to drive a head based upon like spine, neck, head, those poses, when you're going to hit that constellation, I mean, it can be pretty rare when you're being driven by a live human being in a mocap suit that's then going through multiple retargeting steps. So one great thing that was added is the ability to just drive based upon like the head in spine 3 space, like the head vector in a different bone space. And things like that allowed us to fire, like here you can see the poses are dealing with kind of the mastoid and the platysma on the neck. The example I talked about before with the elbow, one of my favorite features of the pose driver, this is really awesome. Anybody that's worked with some kind of radio basis function or pose driver, you can set different fall-offs. You can set like a Euclidean fall-off, linear, you can set a Gaussian fall-off. So instead of, once you set it up, and then we wanted to start adding multiple poses being multiple targets being driven across one single pose, you can go in, and at the end, James allowed us to remap that to a user-definable curve. So I can just go in and look at how all of the different targets are being driven across that pose that I've created, and I can go and I can just hand draw an artistically authored curve on top of the radial basis function. So I don't have to go in and like massage the like Gaussian fall off. I can just go in and artistically draw exactly when I want it fired. You can even do crazy things like draw an S shape, and that'll pump in a specific shape only at the moment you wanted it, and then it'll turn back off. And that's something that's really, really powerful. So we looked at all of the micro detail. We captured so much. 3-lateral's flower scanner captured so much detail of her face, of Binji's face. And then we have to ingest that. We have to break that down into individual things that the rig itself can drive. Because the rig is live, the rig also has to drive all of the different wrinkles. So that meant breaking up the face into a lot of different poses. So here you can see one of the maps that Andrew was talking about before. There are about 120 individually driven blended masks. And here you can see that, yes, the normals are driven, but because the roughness is derived from the normal, we actually get a change in the roughness and a change in the specular. So when she sneers or when she makes some of these larger facial shapes, when the pores flatten out, you get a totally different speck highlight. You get a really kind of broad speck highlight that follows the flattened pores because the pores in the face are flattening. Kind of midway through the project, we realized that we needed a debug view to figure out when all these maps were firing. So this is what some of the guys call like Hulk Andy. But the purpose here was just, we're wiring so much stuff together in the engine, and it's able to handle it, at 60 frames a second and do a really good job, but with just so much complexity that I believe Pete wired together this mode for us to be able to check like every day and daily. It's like, okay, let's just put up the Hulk screen, and we could check that all of the maps were being fired. And here, it not only, it mixes in the color of the masks with the actual wrinkles that are being fired, so you can see each one as it goes off. So the guys authored these maps in 8K. As I said before, it's driving cavity, roughness, speck, normal, diffuse. We talked about kind of the pore flattening and the specular response. There's 40 main wrinkle zones, but across all of those different maps, that's how we get all of the different addressable areas. This is an example of a material function that I wired up, I think, for Senua, because we've been doing zones like this before, but now we've just been using this material function a lot more. I believe we gave this out with the photoreal Twin Blast asset that was available online that you could just download for free. One thing I wanted to mention, in the old days, I would have to resort to some kind of hackiness or wiring a lot of stuff in order to create really big node networks like this. And I will say that in 4.19, which we dropped, there is experimental Python plugin that you can turn on. I thought people would be clapping for that. Woo! I just made Jamie Dale's day there. And that's been a long time coming. I'm sure if you're here to see this talk, this detail-oriented, then that's going to make a difference in your life. And speaking of making a difference in your life, I would like to introduce James Golding. James is the lead programmer who was involved in a lot of this stuff.
Thank you very much, Chris. Thank you very much. So I'm going to speak a little bit today about LiveLink. LiveLink is something that we've used in a lot of these sort of live demos, and it's something we've been working on quite a lot in the last year. So what exactly is it? It's our new system for getting live animation data into the engine. We've been seeing over the last couple of years, more and more people are trying to make applications where they're getting live animation data into the engine for all kinds of reasons. It could be virtual production, it could be for just seeing what they're doing more easily, it could be for location-based experiences, things like that. And we wanted to make it super easy for people to get the information in so that developers could support whatever hardware they were using. We also wanted to make sure that it was a really good experience for users, that they could just plug and play. They could get Unreal to talk directly to any of the kind of peripherals that they might want to use. There's so many cool devices coming out now, like Leap Motion and all kinds of things, where you can get this information very affordably into the engine, and we wanted to make sure this was something that we were really keeping up with. So this is a slightly scary, but I promise it's not too terrifying, block diagram of how the system works. There's kind of three main ways that you can support systems using LiveLink. In 4.19, we release a Maya plugin, which allows Maya to talk directly to Unreal Engine, and you can use it as a preview tool. I'll show that in just a second. But if you have another DCC tool, you can write a plugin for that. This uses our Unreal message bus, which is our sort of protocol for sending animation data. And if you have another package, it should be quite easy for users to create their own plugin for that package that uses the same protocol to send that information into the engine. But maybe you already have a protocol. So a system like Vicon already has a network protocol for sending information, and you want to get that into the engine. So in this case, you write a plugin on the engine side, which will take that information and convert it into our standard live link format. The third option is you might have some peripheral that you want the engine to talk directly to in process, so something like Leap Motion or one of these systems where you're actually using it as part of the final game. This isn't just an editor side feature. It's something that you can use in an actual game to talk directly to peripherals and get that animation information and turn it into a form that the engine can use. So once you've somehow got this information into the live link system, oh, back a sec. Did that work? Maybe it doesn't work. Oh. Once you've got it into the live link system, you can then use a retarget asset to map it from the live link system onto a particular skeletal mesh in a few different situations. It might be an animation node inside an animation graph, or it could be inside the animation tools where you just want to preview what it's going to look like on a particular mesh. And in the future, we'll be using it for things like Sequencer, where we can have Sequencer talking, our cinematics tool, talking directly to the motion capture system for a really smooth workflow. So like I mentioned, in 4.19, we're going to have this Maya plugin, which we'll be distributing with the build. And so you can use this as a sort of live preview. You can have Maya on one window, the engine running on the other. And as you work with the rig in Maya, you can see exactly what the final product is going to look like. You can see how clothing and other simulation is going to work. You can see how the materials are responding. It's great for things like facial animation. We've shown all the detail that goes into it, but you want to be able to see that while you're actually animating. So we think this is going to be a really useful tool for animators. It's something we're using quite a lot internally, even on things like Fortnite when we're putting together marketing shots. It's fantastic to have the animator be able to work and see exactly what the final shot's going to look like with all the lighting and on-set and everything else. Another example is using our Motion Builder plugin, which we're also going to be releasing very soon. This allows Motion Builder to speak directly to the engine, again, over the Unreal Message Bus protocol. This is a short snippet from the Reflections demo we showed earlier on. We used this on set when we were capturing mocap for that particular demo, and it's great to be able to have the actor see whether they're going to be walking through a wall or something live on set. And so again, we can have Motion Builder talking directly to the engine. The retargeting, the more complicated retargeting is done there inside Motion Builder, and it sends the data over to the engine. Also at the show, obviously we've been speaking a lot in this demo about the Siren demo that we're showing. And during that demo, we're actually using two different live link connections. We use one where Vicon speaks directly to the engine. The Shogun software sends its data over the Vicon protocol into the engine. And we have another one where the Cubic Motion Solver sends its data over a different protocol, its own protocol, into the engine, and then we merge those things together. So this was a test shoot we did at Vicon in Oxford a few weeks ago, just to sort of make sure the whole thing worked. But again, this demo is running live link right now, and if you go over to the hall and check out the Vicon booth, you can see it actually running on stage. And they've been having great success with it. This is the blend graph that we use to actually combine those two sources of data. You can see there are two live link nodes on there. So these are not specific to a particular system or protocol. Once the data's into the engine, then it's all treated the same way after that. So the top node is for the body animation. The bottom node is for the facial animation, and we can then combine those together. And as Chris was talking about earlier, once you've got the data, we probably want to use some kind of additional procedural stuff on top of it. Here are some pose drivers. This is a simpler setup than the final one we used. There's only 4 pose drivers, and as Chris was saying, there's quite a lot more used for the full rig. But again, you can take that information, you can run it through. We're also, as part of the pipeline, supporting retargeting, so you can drop in things like iKinema are supporting the system, so you can drop that into the live link, and that can do the retargeting for you if you're doing something more sophisticated. So this is kind of what our year looks like. We've been talking to tons of vendors to try and get lots of support for this system. We want to make sure that the engine is a fantastic place to work with live animation data and to make production really easy if you're trying to build a real-time experience that starts to take this really rich data into the engine. Right now, like I mentioned, in 4.19, we've got the Maya plugin available. iKinema's latest release is also compatible with live link. It'll work right inside that system and retarget if you want to. And we've already shown demos where 3Lateral and Cubic Motion is streaming their data into the engine over live link. We also have the Vicon plugin, which is running on the booth and will be released really shortly. The Motion Builder plugin will also be available shortly. That's something that we've developed. Perception Neuron is going to have support. Xsense are releasing their plugin very shortly. They've been working on that internally and have it up and running, and that'll be great support to talk to those inertial suits. We're also working on camera tracking. That'll come in through the same system. As well as sending just transform data, you can send arbitrary parameters. So cameras can send FOV and exposure settings right into the engine as well. We try to make it really extensible that way. Dynamics is also a facial system which can also send data in over LiveLink. They have another demo running on the Vicon booth if you want to go and check that out, again, running on top of the LiveLink system. Later in the year, Leap Motion are bringing out a new plugin, which will also use LiveLink, running in process to be a much more robust way of getting that data into the engine and doing things with hand animation data. And we're talking to OptiTrack about supporting that system as well later on. We're trying to make it really easy for people to support the system. So we'll be hosting, and for people to get hold of those plugins. So these LiveLink plugins will be available on the marketplace, so you can just download them and have Unreal talk directly to your system. If you're interested in making a plugin, if you've got some system that you want to support, or an external package that you'd like to be able to stream data in from, we'll be having documentation and examples. And of course, the source code for our plugins will be available. If you want to check out the Maya plugin, we'll be running sessions during the show on our booth in the hall, each day, multiple times. And we'll have documentation on how to use it online. So we're super excited about starting to work with all these vendors. We think that the range of options for bringing data into the engine, for bringing these characters to life, we can render such fantastically high-quality characters, and we want to continue to find new ways to bring them to life. So that brings us to the end of the presentation. Thank you so much for coming along today. This is an area that we're super excited about. I mean, you've seen the amazing talent of the people working on this. And do come by our booth. We've got lots more to show, and you can play around with all of these demos on the booth. So have a fantastic show. Thank you so much.